Most people do research, which can be simply defined as gaining knowledge about a particular topic in order to satisfy your curiosity or to achieve some kind of specific goal. Like, I've been doing a lot of research lately on Minecraft. It's my new video game obsession that I've gotten into. And I've spent a lot of time, way too much time, learning about how the various systems and various mobs work and how to build different kinds of things. But scientific research is a different thing entirely. It has some special features that you don't find in other kinds of research. Those features are the fundamental features of science, which is empiricism, systematicity, and repeatability. Now, empiricism refers to the fact that scientific research is only conducted using observable, measurable evidence. In other words, if we can't see it or touch it or taste it or smell it, we can't study it. Like, we have to be able to observe it in some way. That second feature, systematicity, I don't actually think that's a word, but I'm going to pretend it is. But systematicity refers to the fact that scientific research is carefully planned and consistently documented. Scientists need to keep track of everything that happens during their study and every observation that they make in order to be able to accurately describe what they've observed to others. And this will allow the third feature to be possible. That third feature is repeatability. This refers to the fact that if your research is conducted again under the same conditions, you should get the same result. And repeatability is an incredibly important feature in science. It's something I'll go into more detail later, but it's kind of like a quality control. If something happens just one time, it might be a fluke. Or, maybe you did something weird. But if you can get it to happen consistently over and over and over again, that's much more convincing. That's much more obvious that something has happened here. So these fundamental features of science are reflected in what we call the scientific method, which is a method for acquiring knowledge that uses observations to develop a hypothesis. So that observation part, that's the empiricism. And then it uses that hypothesis to make predictions. So we're predicting how things are going to occur in a particular way. That's the systematicity part. And then that hypothesis is tested by making additional observations. So that's the repeatability part. If we can systematically predict how something is going to occur, then we should be able to do that again and again and again and again. And typically, when we do those additional observations, we learn things that we never even expected to learn in the first place. This could lead to the development of an entirely new hypothesis. And so science goes. Science is best thought of as a cycle. It's like a circle. You're always coming up with new ideas. You're always refining your original hypothesis into something more accurate, more all-encompassing, or something more precise. So it's definitely best thought of as a circle. So here's how that circle works. Step one is observation. Observe a behavior, observe some phenomenon that you find interesting. Step two is to try to, in a systematic, planned way, explain how that phenomenon occurs. So this is where you try to state a hypothesis. Step three is to then test your hypothesis. So using your systematic procedure that you've developed, try to determine if your hypothesis seems to be correct or not. Step four is to evaluate your prediction by making systematic, planned observations. That's the data collection phase. And then step five, that's where you use your observations to either support, refute, or refine your original hypothesis, and this is where the cycle begins anew. So we call these like step 1 and 2 and 3 and 4, but as you can see, it's a never-ending process, so it doesn't really make too much sense to think of it in this kind of linear fashion. But yeah, just to elaborate a little bit, step 1, that's where you make those observations. You know, it's usually just a casual observation. You notice something strange on the way to work, or just somebody publishes an account of some weird phenomenon that you find interesting, and you just want to learn more. So that's step 1. That's what gets this whole process started. You could call it like the catalyst. Step 2 is where you try to figure out why this phenomenon is occurring. It's where you read that online news story about some weird thing that happened, and you start speculating, like maybe it happened for this reason, maybe it happened for that reason. So you're trying to provide an answer to this mystery. And the most important aspect of step 2 is to identify what the important variables are. In other words, what seems to be causing this phenomenon to occur. And then, based on the variables that you identify, you will want to create that hypothesis. So, just to be precise, the term variable refers to characteristics or conditions that can change or have different values for different individuals. Like the weather can change, so that's a variable. A person's health status and age are changeable, so those are variables. And they come in 2 basic kinds. Independent variables are ones that are changed or manipulated by the experimenter, like whether you get drug A or drug B, for example. And then there's dependent variables. These are the factors that are observed by the researcher. These are factors that are influenced by the independent variables. So, for example, a researcher could give you a new kind of headache medicine. That's the independent variable, whether they give you the new one or some other headache medicine. And then the dependent variable in this case would be how much of a headache do you have after taking the medicine. So you can see the independent variable influences the dependent variable. That's the relationship that they're looking for. Now, when you identify these 2 variables, you want to start speculating about how they could be related. And that speculation is what we call a hypothesis. A statement that describes or explains a relationship between variables or among variables. And while a hypothesis is an answer to this mystery, you should certainly not think of it as a final answer. It's more of like a tentative, proposal for something that might be true. In fact, many hypotheses are proven to be false, even in successful research, because no matter how good of a tentative explanation you can think of, no matter how clever you are, you can never predict the future with 100% accuracy. You don't know exactly how your study is going to turn out. So while you might be very close to the truth, it's quite common for hypotheses to turn out to be false. And then step 3, that's where you actually, test your hypothesis. You use your hypothesis to make a testable prediction, and then you start developing a procedure to test it. So you want to try to take this general hypothesis, this general prediction about how variables are related, and put it in the real world. Like if your hypothesis, for example, is that swearing can reduce the experience of pain, like if somebody's poking you with a needle and you start swearing, it actually helps. Like if that's your hypothesis, then you could turn that into a testable prediction along the lines of something like participants will be less responsive to a painful stimulus if they're swearing at the same time. So you see, we're just being a bit more specific here. We're putting it in a particular time and place. And then step 4 is the data collection part. So this is where you make those systematic observations. This is where you start to evaluate your results. And the goal is to just provide a fair and unbiased test of your hypothesis. As I already mentioned, it's quite common for hypotheses to not be supported by the data. That's fine. That's part of the procedure. but you need to be honest about it. A lot of researchers feel compelled for various reasons to kind of, get better results, but that defeats the entire point of science. Now, when we do this kind of data analysis to evaluate a hypothesis, it does usually involve that independent variable and seeing how it affects the dependent variable. And along those lines, we need something to compare. So we typically have like an experimental group. So that would be somebody who gets, one level of the independent variable, like the new drug I mentioned. Then we'd also have a control group. So these are the participants who don't get that manipulation we're interested in. And then finally, step 5, that's where you either support your hypothesis or don't. This is where you've collected your data now and you're just comparing your observed results to your hypothesized results. Like, does that tentative answer actually seem to work out? If it does, great. You can write up your report, send it off to publication, and that's the end of that part of the project. You're probably going to want to follow it up with further studies. Research is never done. As I mentioned, it's just a cycle. It just keeps going. But if your data does not support your hypothesis, you kind of have to take a step back. You kind of need to go back to step 2 and start over in a sense. It kind of sounds upsetting, like you wasted time and effort, but when it comes to science, unless you're doing bad work, no time is ever wasted. A hypothesis that is not verified is not a waste of time. In fact, it can be quite enlightening. A lot of researchers, when they try to repeat somebody else's study and they fail to do so, I mentioned before, that's like a quality control. That shows us that maybe that original study did something wrong. So a false result, a failure to support the hypothesis, can actually be really enlightening. But we need to be sure before we start trying to publish these results. So that's basically what science is all about. Science is just about, setting up these testable predictions and seeing if they work out. But there are a lot of misconceptions out there about what science is and how it works. And I just wanted to dispel a few of those. Like, people who are unaware of these methods I've been describing tend to hold certain ideas, which include that science is like a kind of religious system. Another common one is that science is difficult to do. Only highly trained individuals should attempt to do science. And then a third pretty common misconception is that science is a flawed method. There are better methods out there for learning about the world and the people in it. So that first one, that science is a kind of religion, that one, if you just spend a little bit of time thinking about it, and if you have any knowledge of what science is and what scientists do, you'll start to realize this one doesn't really make a lot of sense. Scientific beliefs are fundamentally different from religious beliefs. They both involve belief, like you have to believe in certain things, but those beliefs are not equal. They're held to different standards. Scientific beliefs are based on empiricism and systematicity and repeatability. In other words, we have studied things, we have collected data, we've made observations, and we can present them to you. And then you can, repeat that study and get the same conclusion. You can make the same observations. So that's what makes science special. It's not just like my opinion, it's something I've observed, and now I'm asking you to go observe the same thing. And you can do that. You can go collect the data and come to the same conclusions. So this is completely different from religion. Religious beliefs are often based on faith. Faith is when you hold a belief regardless of a lack of concrete evidence. Most religious beliefs can't be verified through empiricism, and they are very subjective. You can't repeat somebody else's religious discovery. That just doesn't even make sense. It's hard to even put that into a sentence. So you can see what I'm saying here. Science is objective and it's observable, whereas religion tends to be more personal and subjective. That second misconception I mentioned is that science isn't actually hard. You know, a lot of people tend to think science is hard, but it's really not. It's, in fact, so easy that children can do it. People are always going out there to collect data. They're always using those empirical methods. And typically they will alter their hypotheses about how the world works when new information is collected. So in a manner of speaking, people are constantly making observations and updating these hypotheses that they had previously developed about how the world works. So yeah, it's incredibly common. It's just people don't tend to think of that as science. And then that third one is, in a manner of speaking, kind of true. You know, science isn't perfect. It does have some flaws. Obviously, it has limitations. We can only measure observable things. There's a lot of things in existence that may be beyond our ability to observe. We just simply can't possibly in any way measure these kinds of things. So that's quite possible. But for a lot of these unobservable things, we do have ways to get around that. You know, we can develop what are called operational definitions to indirectly measure these unobservable things. Another one is that science requires an observer, and that observer's influence could influence the phenomenon of interest. So maybe the person's biases, maybe just simply the person's presence is going to make an effect, but the fact is putting that person in the situation could change the situation. This is what we call the observer effect. And then the third big limitation is that science literally cannot determine what is true. Truth is beyond the scope of science. Science is all about just forming tentative answers and then seeing if we can support those answers. You know, our answers are never 100% correct. We're always refining our answers to try to get something closer to the truth, but we can never get 100%. You know, we can never get all the way there. And that can be frustrating. It can seem pretty upsetting to a lot of individuals. But to counter a lot of these criticisms, science has constantly been developing new ways to observe phenomenon and new ways to test hypotheses. Like things like X-ray and microscopes and satellites and drones and fMRI, these are all relatively new inventions, but they've unlocked a whole wide range of new techniques that we can employ to test hypotheses that had previously thought to be impossible. So while science may not be perfect, it is incredibly advanced for its age. Compared to other methods of doing research, science is amazing. You know, while science has been advancing all these years, other forms of research really haven't changed at all. They've just been stagnating. Or, as Carl Sagan quoted regarding science, it's not perfect. It can be misused. It's only a tool. But it is by far the best tool we have. Self-correcting, ongoing, applicable to everything. And I definitely agree with that. Science isn't perfect, but it's the best tool we have. But that third criticism I mentioned, that we can never be 100% certain of anything, that can be distressing, as I said. Rarely do we have enough evidence to fully support or to fully evaluate a belief or claim. So as a scientist, you need to develop a tolerance for uncertainty. In other words, there's just things we don't know yet, and we may never know, and you, as a scientist, need to be okay with that. As a scientist, any kind of scientist, like psychological scientist, for example, you need to be able to restrain yourself. Try to withhold judgment on things that we have not thoroughly tested yet, or if there's just simply insufficient evidence to decide. This reminds me of another quote from one of my favorite scientists, Neil deGrasse Tyson. He's famous for saying, "The universe is under no obligation to make sense to you." But that can be upsetting because people want answers. And while we haven't yet answered a lot of the big questions that people really care about, such as where did the universe come from, is there more than one universe out there, or like what's inside a black hole, for example, these are questions I would like answers to as well, but it seems impossible right now. We may in fact never know the answers to these kinds of questions, but that doesn't mean we shouldn't try. Because what seems impossible today could be commonplace tomorrow. We should always try to keep an open mind because we never know what new surprises the future will bring.